In the last video, we got an overview of electrotonic potentials and action potentials and how they essentially can transmit potential differences through a cell, or as how they can move a potential difference through a cell. And just as a bit of review, electrotonic is if you have some type of charge disruption. Let's say a sodium gate opens and a bunch of positive ions flow in. That very quickly is going to make things nearby more positive, right? It's very quickly because the positive charges are going to move away from their positive brethren. The positives and positives repel each other. And so if we go some point further off in the cell, let's say we were looking at that point right here, the positive charges, if they have a positive charge here, it's going to want to move in that direction. If you have a positive charge there, it's going to want to move in this direction. So it's going to become more positive very quickly. So that's what we talk about electrotonic potential. And the benefit is it happens very, very quickly. If we're looking at this point, as soon as these positive charges move in, a positive charge here that's right there is going to want to move there, and the positive charge that's here is going to want to move to the right, but not as quickly because the effect gets diffused, right? The impact on this charge is less than this charge because it's further away. And we could think more. We could run computer simulations about it. But I think you get the general idea. Positive things flow in. Other positive things want to move away. That makes any point that's some distance away from that disruption a little bit more positive. So it'll affect its voltage almost immediately. So it's very fast, but the problem is it dissipates with distance. If we go really far from that, if we went all the way down here, this guy would have almost no impact from what's happening at this opening of this sodium gate. So that's its negative. Now, on the other hand, on the other side of the spectrum, we looked at action potentials. Action potentials are all about you have some stimulus. In general, it's getting a little bit of a positive a charge near a sodium gate. So normally we're resting at minus 70 millivolts. Maybe you have a little bit of a positive charge come, maybe through some type of electrotonic interaction, but that's not enough. But maybe another one comes by and it gets you to minus 55 millivolts, and then the gate opens, sodium floods in, we become much more positive. Then that opens, then the sodium gates close, potassium gates open. Potassium wants to flow out of the cell because we're positive in the cell now, and there's a lot of potassium on the inside because of the sodium potassium pumps. So then we go back to negative. We actually overshoot. And just in case you want to know, at this point we're kind of in this refractory period, and the original gate that just opened and closed, it's deactivated for a short period of time. So there's some period of time that another stimulus won't be able to do it, but then our sodium potassium pumps can get us back to normal. But the whole time that was happening, as the gate that was to the left got all charged up, or as the sodium started flowing in, it's obviously going to make it a little bit more positive to the gate that's right directly to the right of it. So the gate that's to the right of it, its charge is going to go slightly up, and then bam, it hits its threshold for firing. So then that sodium gate opens, and the same thing happens a little bit further to the right. And I could keep doing that, maybe even a little bit further to the right. A gate's potential might look something like that, and that's how it travels. Now the benefit of this is that the signal never loses strength, right? We can just keep going down the cell like this, and we could do that for millions of miles if we had to. The negative is that it's slower than electrotonic, in that you have to open and close these gates, and it also requires energy because you're always having to rebalance the charge potential between the inside and the outside of the cell. So we need to think about, well, gee, how could a cell use both of these things to kind of optimize those trade-offs between a signal dissipation and speed? And this is exactly what the neuron does do. So let's go back. Now we're ready to close the loop and actually talk about the neuron. So when I talked about a neuron getting excited on the dendrite, if I zoom in on a dendrite, let's say this is a dendrite's membrane right here. Let's say, let me zoom in on a dendrite. So that's the dendrite right there. Let's say that this is a drawing of that point right there. When I say stimulated, what's happening is some channel is being triggered, some gate is being opened. And so let's say that this is a sodium channel. And that the stimulus, it could be like in our action potential, it could be voltage gated. If a higher voltage might cause it to happen. It might be some chemical stimulus from some other terminal end of some other axon. It could be pressure. It could be, who knows, it could be some molecule that stimulates it. But something is making a gate open, and maybe it's a sodium gate. And so positive charge is going to flood in here. Positive charge is going to flow into the cell. is going to flow into the cell. And we know why it does that. There's a lot of sodium on the outside. That's what the sodium-potassium pump does. So positive charge flows into the cell. So immediately, it's going to have some impact. If we measure the voltage here, immediately the positive charge here is going to want to travel away. And so this point is going to become a little bit more positive. If we look at this point, it's going to become a little bit more positive, but it's so far away from the original reaction that maybe it doesn't become as positive because it's this the ions are becoming dissipated as we go through the cell. So as we go right here to our axon hillock, we have more gates. We have more gates. Let's say that that's a sodium gate. Let's say that this is a potassium gate. Let's say that we have another sodium gate. It doesn't have to be configured this way. We have another potassium gate right there. Now, if we just had one event here, we're so far away from that event that maybe if we measured the potential at that point at the axon hillock, remember that's a little bulge that turns into the axon. So let's do that. Let's do that same chart that I had before, where we have membrane potential, so potential across the membrane, and then we have time. So if we look at this point, let's say we're looking at this point right here, that point, and we're comparing it to the outside of the membrane. So it's starting at minus 70 millivolts, minus 70, that's its resting. And let's say that some event happened out here, and electrotonically, it's going to increase the potential a little bit, because positive charge is going to make its way, and they're all going to push each other. They all want to get away from each other, and this one's going to become slightly positive. But let's say it only goes to minus 65, nothing happens. Then your ATP or your sodium potassium pumps come into effect, so nothing really happened. It didn't trigger the neuron. But let's say that gets stimulated again, and let's say there's a couple more get stimulated, and their combined effects, because all of them are flooding with positive ions now, their combined effects are enough to get this point to the threshold. So they're enough to get this point to minus 55. And we know what's going to happen here. As soon as this sodium gate gets to minus 55, it's going to open up. It's going to open up, and sodium is going to flood in. Sodium is going to flood in until we get to plus 40. Then it's going to close. But then the potassium gate's going to open and get us back to where we were before. We're going to overshoot a little bit, and then our sodium potassium pump's going to get back to where we wanted. That's going to happen there. But as the potassium is floating in, or as the sodium is floating in into that first gate, this guy is going to become positive here, and then this gate, this sodium gate, is going to become triggered. And this is that action potential idea. Now, we could just keep going our action potential all the way down the axon. Because we said, the benefit of the electrotonic is that it goes fast, but doesn't cover a lot of distance. This is a relatively short distance. This is a short distance. While the axon is super long. So you might say, oh, okay, I see. Electrotonic from the dendrite to the axon hillock. And then we use action potential all the way down the axon. And that would be reasonable, because we're not going to lose our signal strength. We would keep having that that chain reaction going all the way until we get to our terminal end. But the problem there is it's slow. I mean, if this is like a 5-foot-long axon, I don't want to have a slow signal. If someone just bit me, I want to move my hand. If I just touched a stove, I want to move my hand quickly. I don't want all that signal to take so much time, all of these gates to open and close along the whole 4 or 5 feet, or if I'm a dinosaur of my arm. This needs to happen quickly. So what happens is that there's a combination. So what you can imagine I won't make the optical amplifier. Well, I will make the analogy. Is that you get your signal, and this amplifies the signal. The signal is very weak here, right? It only got us to minus 55. But then when that first sodium gate opens, it creates a huge positive potential, and that opens the next gate. So we have a huge positive potential here. Now, the axons have these huge spaces where they're covered up. They're covered up by these Schwann cells or by these myelin sheaths. So even if there are gates underneath them, they're useless. They can't interface with the outside sodiums. They can't interface with the outside sodiums and potassiums. So over this distance of the axon, you cannot have a straight up action potential. But what happened is your action potential here, it made everything a lot more positive than it would have been had there not been that opening of the gate. And now you can have an electrotonic effect again. So you kind of boosted your signal. So now this might get to plus 40. Maybe over here we only get to minus 50. But minus 50 once again is enough to trigger to trigger a sodium gate, which then makes everything really positive again. It boosts the signal. It makes everything positive again. Then your potassium gates, everything comes out of the cell again, so everything gets back to normal. But it boosted the signal. Now electrotonically, this is super positive, but this is super positive. Now the electrotonic effect, if we go some distance down the axon, this will be less positive, but it'll be just enough to trigger another action potential. And then that happens again. So we have this combination of action potentials with electrotonic. So electrotonic, this is very fast. This is a fast interaction. It happens immediately, but it dissipates as it covers distance. So we can't have these nodes of Ranvier being super far from each other. They have to be just far enough so that when one action potential happens, that it's still enough to trigger the next one. It's not going to, boost its potential to plus 40, but as long as it boosts it to minus 55, we're still going to produce a signal to keep moving on. So this is a really good trade-off because we get fast, slow, but it boosts the signal. Fast signal dies down, but it's enough to essentially trigger this guy, and then it boosts the signal. It's slow, but then we travel fast again. Signals dies, boosts the signal slow, and we keep traveling that way down the axon. And this is actually called a saltatory conduction. Let me write this down. Saltatory. It begins with sal. Saltatory conduction, which I think comes from the Latin for hopping. And in a lot of, I remember when I first learned this in biology class, they kind of talked about it. Somehow putting the myelin sheets there just magically made it happen faster, and that these things just hopped from one action potential reaction to another. But that's not what's happening. You're boosting the signal here with an action potential. When these gates open, it becomes super positive. When it becomes super positive here, from a maybe not so positive trigger becomes super positive, that allows this point to become reasonably positive, enough to trigger the next reaction. And when that trigger then becomes super positive, makes this reasonably positive or less negative, it triggers the next one. So it's a combination of action potentials that boost the signal and electrotonic effects that move the signal that gives us this saltatory conduction. So that's actually how neurons are able to make that trade-off between traveling huge distances but not losing their signal.